Hi everyone, welcome to our presentation on the ACL 2022 paper, Generalization by Instruction. This work is done during my internship at Alinei in collaboration with Daniel Kasabi, Chitta Baral and Hana Hajisraji. As you all know, we have several different NLP tasks under the NLP umbrella. In the traditional design pipeline, we often develop datasets to represent this task and then we build models. However, these models often over-rely on these dataset-specific assumptions that prevent them from generalizing to other tasks. And this is a concern because we cannot keep on creating a new model for every new task we can think of. It's because we have so many tasks out there, and there are many more tasks which we have not even defined at this point. And this naturally gives rise to this question: how can you build a system that tackles a variety of language tasks? Now let's say you have three different tasks: pronoun resolution, grammar check, and summary generation. From the multitasking learning literature, we know that the success of multitask learning is dependent on finding commonality across various tasks. Now what motivates our next approach is the intuition that instructions can sufficiently describe a task. For example, in case of pronoun resolution, we can define the task by saying, indicate which character refers to he or she. And similarly, you can have instruction for grammar check and summary generation task. This leads to the hypothesis task instructions are enough to induce sharedness among various tasks. To study this hypothesis, there are majorly two challenges. First of all, lack of benchmark to learn from instruction. And second, it is not clear if models actually benefit from task instruction. And this is precisely what we contribute in this paper, which I am going to show for the remainder of my talk. A quick overview of the paper. We are motivated by the fact that instructions help humans to generalize to unseen tasks. So can we empower machines by allowing them to learn from instruction and subsequently generalize to unseen tasks? We propose an instruction schema to reprint instruction, we collect crowdsourcing instructions and annotations, and curate them to build the natural instruction dataset. We perform an extended set of experiments to find out that instructions indeed improve generalization to unseen tasks. We see a significant gap between performance of our model with respect to performance of supervised learning model, showing that natural instructions has a wide margin to be solved. I'll focus on two aspects: dataset construction, empirical observation. Let's start with dataset construction. We have 61 tasks, 193k instances. Here is how our setup look like. We have a model which is being fed with instructions that define a task. We expect model to follow this instruction, and then for a given input, model should produce the desired output. Rather than creating a dataset from scratch, we thought we will reuse existing datasets because many of those existing datasets are created by crowdsourcing, so they contain crowdsourcing instruction which you can leverage for our purpose. So we ended up contacting dataset authors and got access to their crowdsourcing instructions and annotations. Note that crowdsourcing instructions often involve multiple annotation steps. We divided them into various tasks where each task is a minimal and standalone step in the data creation process. For example, MC Taco, the step 1 is to generate a question on event duration, step 2 is to generate an answer based on the question. So we created 2 tasks out of it, and similarly other tasks. And this is how we converted the 10 datasets we have into 61 tasks. Note that crowdsourcing instructions are HTML documents, and they are written by different people for different purposes. So we need to come up with a way to reprint instruction in a structured format. We did a pilot study. In the pilot study, we tried to find out various common elements across crowdsourcing instructions. And based on that, we developed our instruction schema, which has multiple fields. For example, definition that defines the task. It's a detailed form of instruction. Things to avoid says what models should not do. Emphasis caution says what models should focus on, and we have positive examples that shows a bunch of input-output pairs along with explanations regarding why an example is a positive example. We also have negative examples that shows what are some bad examples. And finally, we have prompt that summarizes instruction. Then we map our crowdsourcing instructions based on our schema. We did several data creation work, for example, removing repetition, creating negative examples, etc. And this is how an example of natural instruction look like. This is the task model to generate a question involving event duration from mstaco. So as you can see, definition clearly defines the task. It defines various terms like what does event duration means, etc. Things to avoid are a bunch of negative instructions. Emphasis and caution is what is important in this task. Positive and negative example. Now for a given text, we expect the model to generate a question involving event duration. Some statistics. We cover 7 categories with diverse set of reasoning skills and diverse set of domains. Let's move on to empirical observation. We use text-to-text architecture, BART and GPT-3. So what you need is an encoding function that converts this instruction and instance to text format. And right now the encoding function we have is that concatenates instruction along with instances. We have varieties of experimental setup. The first one is random split, where we divided our task into training and testing tasks randomly. We also have leave on out setup. For example, in leave on category QG setup, we remove all the question generation tasks from the training split and put it only in the testing split. This means model is never seen to generate question in training time, yet you expect model to generate question at test time, which makes it a hard task. We have rules as the evaluation metric. The blue bar shows the BART performance in the regular multitask learning setup. The green bar shows BART performance in the instruction training setup. As you can see, instructions improve cross-task generalization significantly. We also have GPT-3 performance with instruction. We see that BART, despite being a smaller model, often outperforms GPT-3 instruct. And there is a significant gap between our model and task-specific model performance, showing the scope for future work. We also observe how does model behavior changes as you increase the number of tasks. On the x-axis, we have number of tasks which varies, and the y-axis we have model performance to unseen tasks. The blue bar shows the regular multitask learning performance, that is without instruction. The green line shows the performance of model in the instruction learning setup, that is with instruction. As you can see, model performance doesn't increase significantly in the blue line as you increase the number of observed tasks, but it increases significantly in the green line. This implies that instructions help models to leverage more tasks when they become available. We also perform an ablation study where you use different instruction elements like prompt, definition, etc. In general, adding detailed form of instruction helps, except negative examples, which seem to hurt model performance. And this is in contrast to humans who find negative examples to be helpful. We also study contribution of instruction elements across various tasks like question generation, answer generation. We observe that not all instruction elements contribute equally to model performance, and this depends on the category. For example, in case of question generation tasks, positive examples are very helpful. And this may be because it's easier to define a question generation task by providing a few examples. In case of classification, definition helps a lot. In case of text modification, things to avoid helps a lot. Now to understand this better, we actually conducted a user study where we asked humans by providing them instruction elements and instances, and we asked them to answer this question: which instruction element is important in understanding the task and answering question. We see that humans also find definition to be important for classification and things to avoid to be important for text modification. So machine and human perception matches. We also ask humans to write explanations, where we find that It's actually that the task of classification is undefined without providing definition, because the classes are not clear, and it is indeed hard to learn the classes directly from data without getting access to instruction. The lessons learned: we started with the hypothesis that instructions help humans in generalizing to unseen tasks. Now, can machines generalize to unseen tasks via instruction? We created this natural instruction dataset. We find promise in our empirical result, as you see that instructions indeed help generalize into unseen tasks. However, there are several hurdles for future work. I also want to update that we have recently introduced natural instruction version 2, which scales up natural instruction version 1 from 61 tasks to 1600 tasks. Please have a look at this web page for more information. Thank you.